Greetings to you all, dear students. So we are back again with the last video for the unit design of experiments. And today we are going to focus on the third design, which is called the Latin square design. Now that you have already seen design 1 and 2, which is completely randomized design, also called the one-way classification, and the second design called the randomized block design, which is also called the two-way classification. I'm sure you would guess that Latin square design is a three-way classification. So once you run the slides, I'm sure you will recognize the flow of the problem because it's exactly similar to what we have done in the previous two designs. But this being a square model with very slight differences, we shall see it step by step and again solve three problems as we have done in the previous two videos completely and elaborately to understand the design better. And with this, we shall wind up the unit design of experiments. So let's begin by understanding the features of this design. So the features of the Latin square design goes this way. The complete experimental units that we have, they are divided into an n by n, meaning n rows, n columns square, which we call it as Latin square. If you remember, in the randomized block design, we had a rectangular experimental unit, but here we have the number of rows to be equal to the number of columns. N treatments are repeated n times. So in every row or column, you can see the treatment occurring only once. So if you look at B in that particular row and that particular column, it occurs only in that one place. Similarly, if you take E here, in that particular row and in that particular column, it's the only place it occurs. So every treatment occurs only once in any row and any column. There are three factors, therefore, in our acting which are of interest here, which are rows, and then we have columns. And the third one is the treatment given in every plot. So if you look at this particular example, we have small n, which will be the number of treatments, that is A, B, C, D, E. And here we have 5 rows and 5 columns. So it's a square plot. Experimental units are square type. Total number of plots that we have are 25, and the treatments are assigned in such a way that the treatments occur only once in each row and in each column. So therefore, this is also called a three-way classification since rows, columns, and treatments are of our interest. So since we have three factors studied here, it's called a three-way classification. So making slight differences in the RBD model that we had, we shall proceed further similarly in the further slides. So this slide talks about the merits, demerits, and the difference between LSD and RBD. I'm sure once you read it, it is very clear. Merits of LSD are it controls the variation in 2 dimensions and thus reducing the experimental error. And even if observations are missing, experiments analysis can be done. Demerits is it is restricted. The shape of the experimental design is a square, so it cannot be rectangular. Process of randomization is not simple because we want the treatments to be allocated in such a way that it occurs only once in each row and in each column. It's preferable only for small number of treatments, and 2 by 2 Latin square design is not possible due to these restrictions. So these are some of the demerits of LSD and these are the merits. LSD and RBD, we are well aware what could be the differences. Number of rows and columns have to be equal in an LSD, whereas there's no such restriction in RBD. And LSD, it is suitable for small number of treatments. There is no such restriction even in RBD. Variation is controlled in 2 directions, whereas in RBD it's only in 1 direction. It's called LSD is a three-way classification where row, column, and treatment are of our interest here. Whereas in RBD, we had only block and treatment to be of our great interest, and so we called it to be a two-way classification design. So this is an obvious difference between LSD and RSD. And now let's move forward to construct the ANOVA, etc. So let's now talk about the ANOVA table for a three-factor analysis. As we just discussed, the number of treatments is equal to the number of replications. So totally we have, if you take n to be the treatments, capital N, the total number of experimental units will be n square, and it is so arranged that each treatment occurs only once along each row and column. So that's the most important factor. So how do we define the null hypothesis? We'll have to check the difference between the rows, check the difference between columns, and check the difference between treatments. So these are the three parameters which are of interest. So we'll have three statements for the null hypothesis, that there is no significant difference between the three. And we have alternate hypothesis where we say there is significant difference between. The rows is one, columns is the second, and treatments is the third. So we shall go to the next step in the next slide. Now, as you are aware now that we have three factors to be discussing, but we cannot construct a three-way table on a paper. So we shall construct a two-way table first and a one directional table, just as we did in the first design, which is completely randomized design. So in order to analyze the three factors, we shall have a two-way table and a one-way table. So when I draw the two-way table based on rows and columns, so the rows are written along the column here. So these are the rows and these are the respective columns. Here I have an n by n square matrix. That is what I get. Ri represents the total yield row wise. Ri square, the number of plots in that particular row, which is n. Then I divide Ri square by n. So this gives me the mean yield along the rows. Similarly, Ci is the total yield column wise. So when I take the total yield row wise or column wise, what I get is a grand total, which is G. The same notation has been followed even in the earlier designs. Then I square the column totals. N is the number of rows that I have for every column. So because n and earlier we had k here and we had the t here, we had r here, if you remember, for t's. So here we are calling ri and ci just to represent them as row total and column total. And n is the total number of rows, number of columns, which is the same. So capital N will therefore be equal. And then we calculate the mean yield along the columns, which is Ci square by n, the total of it, which is represented here. So it's a fairly easy table to remember once you have done RBD. Now this is just a two-way table. We have only considered the rows and columns. So there's still one more parameter to be constructed, which is the treatments. So that we shall consider in a one-way table, just like how we did in CRD, which I'll show it to you in the next slide. So the third factor, which is treatments, we treat that in the CRD style by writing down the treatments along the first column, the yield which we shall pick out from the two-way table, and then the TI, the total yield, row wise, then Ti square, which you square them. Note that the value of G that you get here should be the same as what G you get in the two-way table. Similarly, the total n that we write should match with the total n in the two-way table. And finally, when I divide Ti square by n, I get the mean yield along based on the treatments as sigma Ti square divided by n. So sigma Ri square by n, as we got in the two-way table, represents the mean yield between rows. Then sigma Ci square by n will give me the mean yield between columns. And sigma Ti square by n is the mean yield based on the treatments. Let us now decide the various sum of squares, this we know as before. The first one being total sum of squares, double sigma the square of the yields minus the correction factor g square by n. Now we need to find the total sum of rows, sum of squares row wise. We call it SS row. And when we are talking about row wise, we take this total sum along the mean yield along the rows. So it's sigma Ri square by n. Then between the column sum of squares, we column them as SS column and define them as sigma Ci square by n minus the correction factor. And we have between treatment sum of squares, which is SS treat, sigma Ti square by n minus G square by n. And the SS error would be the total sum of squares minus these three values that will be found. And now that we have the various sum of squares, we are now ready to draw the ANOVA table and carry these values that we have found to the table. So this is the ANOVA table for the three-factor analysis. The rows that we write are exactly the same as what we discussed before. Source of variation, degrees of freedom, sum of squares, mean squares, and variance ratio. The rows extend by one more because we are talking between rows, between columns, between treatments, as we have three factors. Then, of course, the error and the total. So between the errors, between rows, columns, or treatments, the degrees of freedom are n minus 1 each, and the error is n minus 1 into n minus 2. The sum of squares is what we calculate earlier in the earlier step. We divide the sum of squares by the respective degrees of freedom and then calculate the f values for the row by error, the column by error, and treatment by error. So we get three f values. We are calling them as f1, f2, and f3. We shall now compare them with the table values based on the degrees of freedom and then conclude our result. So our comparison is the same. The calculated value of f1, f2, f3 with the table value. If it is less than the table value, then we accept H naught, that is a null hypothesis, else we reject the H naught or accept the alternative hypothesis. Now let's read first problem. The following data resulted from an experiment to compare three burners, B1, B2, and B3. A Latin square design was used as the tests were made on three engines and was spread over 3 days. Test the hypothesis that there is no significant difference between the burners. So if you read the question carefully, we are talking about an experiment to compare three burners. And for that, what is it being done? The tests are done on three engines and 3 days. So you see everywhere you have the number 3. So your n value, small n value, is equal to 3. Small n is equal to 3. So your capital N in this case, which will be n square, is equal to 9. You're talking about three burners, you're talking about three engines, and you're talking about 3 days. And the table given to you here has engines along the row. Here you see this is engine 1, engine 2, engine 3, and days along the rows. So what we normally do in our theory, we call them as rows, columns, and treatments. So days here are rows, engines are here columns, and this B1, B2, B3s, these are nothing but treatments which we are given. So we are given three factors, and so the problem is a Latin square design. And we are also given the treatments in such a way that B1 does not repeat. One particular treatment does not repeat in a particular row or column. So therefore, now though the question asked here is no difference between the burners alone is asked, but we are doing the problem for both rows, columns as well as burners. So in the normal sense, we write the null hypothesis that there is no significant difference between the rows, columns and treatments. We shall write within brackets pertaining to the problem we are studying. So the rows are nothing but days, columns are engines, treatments are burners. An alternative hypothesis, there is significant difference, and we define the level of significance to be 5%. So therefore, now we shall proceed by rearranging the data. As I said, we are talking about a three-way table which we cannot draw directly. So we draw one two-way table and one one-way table. So let's draw the two-way table based on rows and columns, which are days and engines. So we have drawn the two-way table here. The rows are taken up. The columns are engines. The rows are days. So I'm writing D1, D2, D3, E1, E2, E3. And these burners, which the treatments that we have given, I keep them as it is and write beside them a number. What did I do to the number now, which was actually 16 here? Why did it become 0? Because I wanted to decrease the complexity of the numbers. So I subtracted each cell value by 16. And therefore 16 minus 16 became 0, 17 minus 16 became 1, and so on. So I got the values of all the 9 points in a simplified manner by subtracting 16 from the given cell values. Then I take the row wise total. So it's 0 plus 4, 1 plus 4, etc. So I get the row total to be 1. Same way I take the column totals. So the row total and the column total both give me G equal to 1. I square the row values, the column values. N value here is 3 for both. So because the number of rows, columns all are 3. So I put them to be 3. So the N, capital N, as I discussed, is N square and it coincides with 9. I divide Ri square by N to get the mean row value and divide Ci square by N to get the mean column value, and that is the values which I will be choosing taking ahead for calculating SS row and SS column. But before we do the sum of squares, we have only drawn the two-way table here. Let's take these treatments and frame a separate one-way table. Now the treatments which I will write it as B1 here, B2 here, B3 here. So what would be the yield that I write as? See, look at the first row. B1 has the value 0. B1 in the second row has the value -1. B1 has a third row -4. So in the yield column, you will write 0, -1, -4 for the treatment B1. And similarly for B2, 1, 0, -3. For B3, it will become 4, 5, and -1. So we shall write it this way and then proceed. So as I explained to you, we are rearranging the data based on the treatments, and the yield is written as how B1 occurs in the three rows. You can also take it column wise. There is no difference. Then I take the total yield. Look at the value of G. G is 1. G was 1 even in my two-way table. Ti square, capital N value is 9. I divide Ti square by N and I get the mean treatment value. So I now have sigma Ri square by N, sigma Ci square by N, sigma Ti square by N. Now comes the fine calculation of sum of squares. So I calculate the total sum of squares first by squaring all the yields and adding them up, subtracting the correction factor. Then I calculate SS row by taking the row mean minus the correction factor. SS column is the column mean minus the correction factor. SS treat is the treatment mean minus the correction factor. And the error is SST minus all these three values. And that gives me the error as 1.55. Let's substitute this in our ANOVA table now. So we frame the ANOVA table, source of variation, which will be between rows, that is days, between columns, that is engines, between treatments here, it's burners, error, and total. Degrees of freedom is n minus 1 in the first three cases, n is 3, so it is 2 in all the three cases. Error is n minus 1 into n minus 2, so it is 2. The total is capital N minus 1. N is 9, so it's 8. It definitely agrees with 2 plus 2 plus 2 plus 2. Same manner, sum of squares, R1 is SS row, R2 is SS column, R3 is SS street, and R4 is SS error. When we add all of them, we should get SST, and it does coincide. Now I calculate MS row. I divide R1 by 2, then MS column, R2 by 2, MS street, R3 by 2, MS error, R4 by 2. Then I pick out from MS row and MS error, whichever is the largest. I take that in the numerator and the other in the denominator to get F1 value. F1 value is the calculated value along the rows. Similarly, F2 will be along the column, so 0.78 by 0.78. And a treatment, for with respect to treatment, F3 will be MS treat by MS error. Now we shall compare that calculated value with the table value with the degrees of freedom as 2, 2, because all the degrees of freedom are 2. We shall take it from the table value and compare and see what the conclusion is. Now look at the table value for 2, 2 degrees of freedom. It is 19. So F1, which is 22.51, is greater than 19. So our H01 is rejected, meaning we are accepting the alternative hypothesis H11. So there is significant difference between the days. Next would be when I take the compare F2 with respect to the table value, it is less. So I accept the null hypothesis, meaning there is no significant difference between the columns. And finally, the question that is asked is only with respect to the burners, though we did the other two also. So 19.93 is the value. It is greater than 19. So I reject H03 and I say there is a significant difference between the treatments, which in our case is the burners. So difference in burners does show a difference in the yield. So therefore, that's our basic conclusion. But since rows and columns we did not omit here, we did that part also as an additional part in this particular problem. Let's look at the second problem now. Reading the question, analyze the variance in the following Latin square of yields of paddy, where A, B, C, D denote the different methods of cultivation. Examine whether the different methods of cultivation have given significantly different yields. So he says analyze the variance in the following Latin square of yield. So what is given to us is the yield of paddy, and ABCD is the treatment that is applied. Treatment is nothing but here different methods of cultivation. Whereas we do not know what these rows represent or columns represent. So we shall treat it unlike in the previous problem where we were given days, engines and treatment. Here, since we are not given explicitly what are the rows and columns, we shall treat it as rows, columns and treatments representing methods of cultivation. So using a particular method of cultivation, the yield is specified in each plot. And as you see here, the value of n that we have is 4 because we have 4 rows and 4 columns. So capital N, which is n square, becomes 16. So we shall repeat the problem by taking rows, columns and methods of cultivation to be our parameters. The level of significance continues to be 5%. So I construct the two-way table here, and as I do not know what are the rows and columns, so I write them as R1, R2, R3, R4. If you remember, in the earlier problem, rows were days, so we wrote D1, D2, D3. Here it is rows and columns. So I calculate the row total, the square of them, and I have n plots, that is 4 plots for every row. I divide Ri square by n, calculate the total. I get the grand total to be 30 here, and capital N, as we decided, it is 16. In the same lines, I calculate the value that I am given. Now, if you note the value there, I write D2, but actually it was 122 if you recall. So what have I done? I've simplified the values just like how I did in the previous problem, where the cell value is subtracted from by 120. So I am taking the difference of one existing cell value minus 120. 122 minus 120 is 2. 121 minus 120 is 1. So thereby all these 16 values reduces considerably, and which makes my computation easier. So then I calculate Ci square, then n is 4 anyway for every column, and I define Ci square by n and get the total mean value along the column. So I know G, I know N. Note that G is 30. So when I'm constructing the one-way table also, I should have G to coincide with 30. N is 16. And then we shall calculate sigma Ti square divided by N. So I construct the one-way table keeping in mind methods of cultivation, which is the treatments. I take up the value, the yield that this treatment shows based on the 4 rows as 1, 2, 0, 2, etc. from the two-way table. Then I calculate Ti. Note that the G value should give me the same 30, just as we recall. Then I square Ti. N is 4 everywhere, so capital N is 16. I divide it by each by n and take the summation. It gives me the mean values along the treatments, which is the methods of cultivation. Now all the data are available. We shall carry it forward into the ANOVA table. So we compute the sum of squares as we did earlier, calculate SST, SS row, making use of the mean row value, and then SS column, SS treatment, and then I get all the differences by subtracting them from by the correction factors, and by subtracting SST from all the three, I get the SS error values. Now I carry forward it into the ANOVA table. So this is my ANOVA table. Now, first source of variation is between rows. We do not have a special name for rows. So between columns and between treatments, which is methods of cultivation, we have n to be 4. So therefore, the values are 3 each. N minus 1 into n minus 2 gives me 6. The total is capital N minus 1 is 15, which coincides with 6 plus 3 plus 3 plus 3. Similarly, R1 is SS row, R2 is SS column, R3 is SS treatments, and R4 is SS error. We divide each of them by the degrees of freedom to get the mean squares and divide the row value row by MS error, MS column by MS error, and MS treatment by MS error, where all those values are greater than MS error. Compare it with the table value with 3, 6 degrees of freedom, because 6 is my degrees of freedom for the error, and then make our final conclusions. So we find that the table value for 3, 6 degrees of freedom at 5% level of significance is 4.76. We find the first value is greater than the table value, so we reject the null hypothesis and accept H11. So there is significant difference between the rows. Second value is less than the table value, so I accept H naught, saying there's no significant difference between the columns. The third value, which is 2.12, is less than 4.176. That's the table value. So I accept H naught and I say there is no difference between the treatments, which is the methods of cultivation. The question here too was asked only with regard to the treatments and not with regard to the rows or columns. But as a practice, we have done for all the three. But the main answer is the last one. So there is a difference in the yield of paddy based on the methods of cultivation. Let's look into problem number 3 now. Problem number 3 is given in a very simple way. It says analyze the variance for the following Latin square design. So there is nothing spoken about what are A, B, C, D, what are the rows, what are the columns representing. So there is no, it's a very vague kind of a picture given to us. So therefore, we shall treat the three parameters as rows, columns, and treatments. In the earlier problem, at least we knew what was treatments, but here there is no mention of that. So we will assume it to be rows, columns, treatments, and proceed exactly in the same manner after defining null hypothesis, alternate hypothesis, and level of significance. So I am constructing the two-way table here once again by writing the rows and columns. And I have subtracted each cell value by 18. So the cell value minus 18 is what I have written so that I simplify the seriousness of the numbers. It was quite large. Now I added it to get the grand total to be 20. And since my small n is 4, once again, my total capital N is 16. I calculate the mean row values and the mean column values and take it further. Now let's utilize the treatments or rearrange it based on the treatment. So the treatments will be A, B, C, D. And if you note, the yield will be 2, 1, minus 4, minus 3 in the first row, 5, 0, 1, and 3 in the second row, and likewise the other two. Let's see how it is done in the next slide. So as I said, we are rearranging it for the treatment given. For the treatment A, it is 2, 1, minus 4, minus 3. By taking the treatment A application along 4 rows, we calculated Ti square, N, added up, took the mean treatment values. Now we have found all of them. Let's calculate the sum of squares after we know the values of G, N, and the three mean values. So we have found the total sum of squares by calculating the total sum of the squares of the yields, and then using the means, the three means, subtracting the correction factor, we have found the three values, and by subtracting the SS row, SS column, and SS treatment from the main SST, we get SS error. Now we shall apply all this, substitute all this in the ANOVA table and make the required conclusions. So the source of variation in this table will just be between rows, between columns, between treatments, because we do not know explicitly what they mention. And here again, as we have 4 as n, we have a total to be 15. We have substituted for the 4 sum of squares and checked it to be equal to SST, divided the MS row I got the MS row by dividing R1 by 3, etc. And all the four mean squares divided the F1 to get F1. We divided MS row by MS error. Similarly, got F2 and F3 values, compared it with the table values, and concluded in my next slide. The table value is 4.76, which was the same even for the previous problem. We find that the F1 value is greater than the table value, so we are accepting the alternate hypothesis H11. So we say there is a significant row difference between the rows, whereas the F2 value is less, so I'm accepting the null hypothesis. F3 value is greater, and therefore we accept the alternate hypothesis and reject the null hypothesis. So there is a significant difference between the treatments. There was no mention about what is to be found because the question just said analyze the variance. So here all the three results matter. So it is better we analyze it for all the parameters to be on the safer side. So this comes to the end of unit 5, which was design of experiments. We have discussed all the three designs, basic designs, which gives us an idea of creating any more designs, and the way ANOVA helps us, and the F test which helps us in deciding whether there is significant difference between certain parameters. So I hope you all have understood all the three designs, and will work out a few more problems by looking into standard books, statistical books, give you a lot of such problems. The basic problem here is to identify when you read a theoretical question. The main aim here would be to recognize what kind of design does the problem relate to, and thereby apply that particular procedure in order to make the required conclusions. So please attempt a few more problems. I could just give you three problems here. Maybe you could pull out some more problems from standard statistical books and then practice them and thorough your concepts in design of experiments. We shall do the next unit from the next class directly. So I shall bring out some videos on those topics too very soon. Take care. All the very best. Goodbye.